Transformer architecture has changed the face of artificial intelligence. The transformer architecture is really powerful but notoriously slow. Researchers have developed numerous tweaks to accelerate it, but now researchers are looking at alternative works to enhance the strength and dampen the weaknesses of this transformer architecture. In this research paper, which you can see on your screen, Quentin Fournier, Gaétan, and their colleagues have surveyed variations on the transformers, and they have evaluated methods designed to make it faster and more efficient. If you have heard of transformers, you must have heard of attention mechanism too. The attention mechanism in the original transformer places a huge burden on computation and memory. On the cost of the length of the input sequence, we know that there are a lot of variables. As a transformer process each token in an input sequence, it concurrently processes or attends to every other token in the sequence. Attention is calculated by multiplying two large matrices of weights before passing the result matrix through a softmax function. The softmax function normalizes the matrix values to a probability distribution, bringing higher values closer to 1 and lower values near 0. This enables the transformer when encoding a token to use relevant tokens and ignore irrelevant tokens. Now, if you look at the paper in detail, they have described this attention mechanism here in great detail, which I just summarized for you. And if you scroll down, there are a lot of other things around encoders, decoders, complexity, and so on. Then they discuss some of the general approaches. And in these general approaches, they have given a great detail to a lot of options here and a really good read, I would say. And if you scroll down more, you will see a lot of discussions around strategies around parameter initialization. Now, these approaches simplify the attention calculation by using a subset of weights and setting the rest to zero. They mix and match three general patterns in which the position of a given token in a sequence determines how it attends to other tokens. I'm not going to go into the detail of these strategies. I will let you read it and I will drop the link in video's description. But what I want to say here is that all of these strategies and variations, they can really help machine learning engineers manage compute requirements while taking advantage of the state of the art approaches. So I'm very excited about this research and I'm really keen to know your thoughts. As if in the course of doing this machine learning, are you doing any trade-offs? Are you using any variations or have you developed any of your own strategy to optimize the transformer architecture? I hope that you liked it. If you like the content, please consider subscribing to the channel. Thank you very much.